talk is I'll give you some motivation for why we want to study the system and the structure of how we walk. And then I'll go on to the main physical principle governing it, which is the competition between minimizing the energy and maximizing the stability, similarly to what you have in statistical mechanics, where you have to minimize the free energy, which is maximizing the entropy and minimizing the free energy, true energy. And lastly, I'll go on to discuss a simple model for studying the stability of some perturbed motions. So why do we want to study the way we walk? Well, for me, it was just curiosity. I was really curious how it happens that we walk the way we walk. But for practical purposes, we kind of want to know if something happens, something bad happens to us, so we say lose a leg or whatever. We want to know how to approach rehabilitation by knowing how to walk properly. And we have to be able to quantify that in some way. And the other approach is that we're building more and more humanoid-looking robots so that they could help us do some of the work that we're supposed to do. And it would help for them to have stability for walking at quite higher speeds than they actually do now. So this is a bit of text, but I'll first focus on why we can say that energy is minimized while we walk. So once we consider the so-called vertical ground reaction forces of when we walk, it kind of allows you to define an action function. And if you want to, I can explain what this actually means later on, in the question session. And once you have that, it kind of allows us to draw a graph of the deviation of the ground reaction forces during a single stride cycle. So the way it happens is that if the whole stride cycle is just going 2 steps, and it seems that the deviation of the reaction forces is the smallest at the half of the stride time. So once we look at the change in kinetic energy and potential energy, and the gravitational potential energy doesn't change in a whole cycle because we go up and down. So the only thing is the kinetic energy. So it turns out that the kinetic energy has the minimum also at half stride time. So if we walked the way as to, say, I do the half step, and then the next part starts exactly at half time, it minimizes the energy. And it turns out experimentally that we do. So we can say that the way we walk is governed by a principle of least action. So, I mean, I said least action and minimizing energy, but where's the stability in that? So we know that apart from minimizing the action or energy, we want to also maintain some stability while walking. And it's actually not clear how it actually happens, what's the relative importance of stability and minimizing energy. So to be able to study this, we have to somehow destabilize our motion and study it there. So the simplest choice is walking downhill. And experimentally, once we do that, it turns out that we prefer a more stable gait to that of minimized energy. And, well, can we quantify this in somehow? So as physicists, we like simple models. So we consider the simplest model of all, which is called the dynamic walker. It's based on a toy that was built in the 19th century. It's basically a mass connected with 2 legs, which are massless, and 2 massive feet. And works, if it goes down the slope, it just works by using direct gravity. The motion of this toy, of this walker, is 2-phased. So there's a continuous leg swing and a discrete foot strike. It's a rather simple model, so we can write a Hamiltonian for it, which isn't overly complicated. And just for further purposes, I'll kind of define a vector of angles and angular momenta. So we have the swing phase, and what about the foot strike, which is a discrete event of sorts? So it's not really discrete, but for simulating it, you can assume it's discrete. So the way we do it is we consider that it is an elastic collision, and we just say that we have to have the angular momentum conserved. And it happens actually at a particular set of angles between the legs and the normal to the floor. And actually, the resultant equations of motion aren't that enlightening, and they're quite complicated. So instead of showing you what they are, I kind of try to plot the solution in phase space. It's actually a 4-dimensional phase space, so you can't really plot it in 3 dimensions. So this is a simplified curve, which is in 3 dimensions. And so if we want to study the stability of this problem, we won't study the stability of how we walk, we'll study the stability of solutions in the phase space. And to simplify this very complicated continuous motion, we'll introduce something that's called Poincare sections, which are hypersurfaces, and a Poincare map. So if we have a solution that kind of orbits, then it intersects at the Poincare section at some point. And to get the next intersection, at the section, to get the next point where it intersects, we apply the so-called Poincare map. And we got a selection of points like here, 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 and here. And it allows us to simplify the problem of studying stability to a discrete event rather than continuous one. So obviously, the simplest solution is a stable solution, which is the blue curve. But around it, if you notice, there's like small light blue curves which don't close on each other but seem stable. But how do we quantify this? We need some criteria for studying it. So there's 2 actually. There's orbital stability, and we look at the intersections. And if the points stay close to the equilibrium, we say that the motion is stable. Otherwise, it's unstable. So a more quantified way is we estimate the Jacobian of the Poincare map and find its eigenvalues. And if any of the eigenvalues has a value that is greater than 1, then the system is unstable and we fall over. But this is really a discrete set, and we kind of lose some information about the stability of the system. So we want to study the local dynamic stability. And say that our system is described by an equation of motion, and this is a complicated bit. Then we want to look at the eigenvalues of the Jacobian of this complicated bit, which is basically a derivative, the Jacobian, so the derivatives of this, say, force at the equilibrium solution. And once we find the eigenvalues of it, if all of the real parts of the eigenvalues of this matrix are less than 0 at some particular time t in this whole solution, then we say that at that time the solution is locally stable. And otherwise, we say that it's locally unstable. So what does it mean to be locally stable or unstable and orbitally stable? So I mean, we can have points where kind of get stability locally, so the motion is more stable at that point and less stable, say, at this point, but can still be orbitally stable. So it's really hard to imagine it. So the way you can think of it is, once you have an orbitally stable motion, you won't fall over, but you will have this nice feature of the fact that if something is locally stable, then you can minimize energy at this point. And once it's locally unstable, you have to get some extra energy to recover from falling over. So this is a nice way of studying this system. And now I'll summarize. So we've learned that human gait is governed by trying to minimize the energy costs of walking and maximize the stability at the same time. So the relative importance of the 2 isn't really known. So we have to study some perturbed systems. And it turns out that experimental results support most of the results and the predictions of the simplified models. So actually, the dynamic walker, without having any of the springs and pelvis movement and so on, it turns out that it gives you qualitatively very similar answers to how we walk downhill. I think that would be all. Thank you. So if there's no questions, I have a video for you how far we've gotten with robots walking. And if there are questions, then I'll answer it. So I can just put the video on, and you ask questions. I'm not sure how fast it's going to be in here, but okay. So ask questions, and this is going to run in the background. Yeah? So there is a slope, and it has these two legs that kind of swing. So there's this, kind of axis about which the legs can rotate. And if the slope is big enough, and it doesn't have to be big enough, once you start one leg moving, then it constantly just moves down. So the way you do it actually is you have to build it quite nicely. But you can get those toys somewhere probably. I mean, they were built in the 19th century the first time, like 30 years before people thought of robots. So if we study stability, we can kind of, this is one of the results of studying stability of motion.
Wait, actually, I did want to ask.
Yeah.
Is there some natural speed at which you just cross over from walking to running?
So I think it's the moment where if you would somehow have to, I haven't studied running because it's quite different. So there are papers that study either running or walking. It seems there's some qualitative difference. So you have to jump in running, which is a bit different event. And actually, there's actually a lot more papers on how cockroaches run than how humans run. So it's a bit easier probably to study it.
Yeah, so I wonder, because when I walk, my wife has longer legs than I do, so when she walks fast, I have a hard time keeping up with her. It's very uncomfortable. But on the other hand, just running slowly is so easy.
Yeah, so...
Right? So there's a natural, seems like a natural transition.
Probably. I mean, it's slightly different than, so you have this kind of, you have to use muscles differently, so you can't really do it using those simple simulations, where the simple model where you can just kind of walk. So you have to have this kind of springing motion and running. So I don't know whether you know this athlete who runs on these artificial legs. So this is very simple to actually simulate, because those legs actually work like cockroaches' legs. So there are models for it, but I mean the Lagrangians and Hamiltonians of that is, I mean, quite a bit more complicated, because you have to have this kind of up and down motion as well. So I mean, there are actually Lagrangians for a more human system where you have 7 independently moving parts, like the pelvis, the knees, and ankles, and so on. The Lagrangian for it is immense, and you can't really do anything analytic with it.